Okay, good morning. Today, what I'm going to do is I'm going to work on the next section of chapter 5. And so what we did when we spoke last week was we looked at some introduction to energy. So we talked about internal energy or energy. We talked about heat. We talked about work. We're going to go a little bit more into detail into heat and work today and connect that to something called enthalpy. So let's remind ourselves. Oops, got two people here. So let's remind ourselves a little bit about the energy terms that we're using. Okay, so there's several terms that you want to be aware of. So the first is called internal energy. Okay, internal energy is typically a capital E or a capital U. Both terms are used, just depends on the textbook that you're using. For this discussion, I will use E. Okay. Now, really what we're interested in under most circumstances is what we call the change in internal energy. Not the actual value of the energy, but the changes that occur. How much energy comes in, how much energy goes out. And for that, we're going to use, again, you could use E or U, but I'm going to stay with the E. So I'm going to call this delta E. And that is the final value of the internal energy, F for final, minus the initial amount of internal energy, initial I, okay? So final energy minus initial energy. You can think of this in the following way. It's a common introduction to this topic is to imagine that you got a bunch of gas molecules bouncing around in a balloon and they have energy, right? They're bouncing around there, they're interacting with each other, they have energy. So essentially the energy, the internal energy, is a measure of the energy that these molecules have in the container. Okay, that's essentially what the internal energy is. So if we somehow put energy into this gas, okay, the gas will have more energy. And so we would have a change in energy. Or we could withdraw energy from the gas. Again, you would have a change in energy, right? So we do have a sign convention. When we add energy to the gas, delta E is positive. It's a positive change in energy. When we remove energy from the gas, GAS, delta E is negative. Okay, that's a negative change in energy, right? And in general, this is not completely the case, but in general, we consider two ways of adding or removing energy from the types of systems that we'll be interested in, which would be gases or chemical reactions, that sort of thing. So two ways to add or remove energy. Okay, to the gas. And that is heat, which we call Q, and work, which we call W. And so we can put this into a very simple mathematical relation. And what this says is the change in the internal energy of a system, we're going to use the term system is the gas, right? The change in the internal energy is just equal to the amount of heat that is added or removed from the gas plus the amount of work that is done on the gas or by the gas, right? So we talked a lot about that. You can refer back to the previous lecture about the sign convention for heat and work and the terminology of doing work on the gas or on the system or having the gas do work on the surroundings. Work is done by the gas, okay? So there is our relation. Now, what we're gonna do at the beginning of today is we're gonna talk a little bit about this term here, work. And we're going to have a mathematical equation to discuss work. And it's a relatively simple equation. And so let me go ahead and write this down. This is really what we would call mechanical work, or sometimes it's called PV work, pressure volume. P is pressure, and V is volume. Okay, it's called PV work. And that is based on this gas cylinder problem that we looked at last week. So remember, you have this gas cylinder, so you have a piston holding the gas in a cylinder. So there's your piston. Okay, here's your cylinder. And then you got your gas or mixture of gases inside the cylinder. Okay, so that cylinder has a volume, right? The cylinder has a volume, and the piston can apply a pressure to the gas. And in general, what happens is the piston applies a pressure, but once the volume of the gas equilibrates or comes to some form of stability, the gases will apply the same pressure to the piston that the piston applies to the gases. So we'll say this at equilibrium. So equilibrium is essentially a measure of stability. So when it's stable, the pressure applied by the piston is equal to the pressure applied by the gas or the gases in the cylinder. Okay, so let's talk about that for a moment before I do the calculation. We have this concept in physics of something called a force, right? And we can represent forces as having directions. They're called vectors, okay? So we can apply a force. And in general, if we're talking about how much something weighs, when we talk about its weight, weight is a force. It's a type of force. And so let's talk about an example of force, which is called weight. So W is equal to the mass, so M, times the gravitational acceleration of the Earth, which is G. Okay, so weight is an example of force. M is equal to mass. And G is a constant. And this is called the gravitational acceleration of the Earth. Okay, so mg, very simple relation. So if I have a mass, let's say a brick, for example, a mass on the Earth would have a weight, and the weight would be equal to the mass of the brick times the gravitational acceleration of the Earth. So now imagine that I balance that mass on this piston. So I'm drawing the piston a little bit bigger. Okay, so here are the gases in here. Okay, that mass has weight, so it's applying a force on the gases. It's pushing down on the piston. It's pushing down on this membrane. But what happens is eventually the gases will apply the same force upward. So what you'll end up with is a force downward due to the weight and a force upward due to the gases. And if this piston is stationary, meaning if it stops moving, it's not moving at all, that would just tell us that the weight is equal to the force that the gases are applying on the piston. So at equilibrium again, the weight is equal to the force of the gases. Okay. Now, if you put more mass on, you would be changing the weight, and that would compress the gases. On the other hand, if you took the weight off, now the force upward from the gases would be greater than the weight, so it would move up. The piston would move up. Okay, so that allows it to move back and forth. Okay, now let's define something called pressure. Pressure is related to force, and it's equal to the applied force, so the amount of force that you have, divided by its surface area. Okay, so looking at this cylinder from, this perspective. So if we're looking down on it, what you would see is you would see the cylinder, and then you would see this mass on it, right? So you're looking downward on it. That cylinder has an area. It's a circle, right? Pi r squared. So what we can do is we can define the pressure as being the force that we're applying due to this mass, due to its weight, divided by the surface area of the cylinder. Okay, it's kind of cool. So that's pressure. Now, what we're going to claim here is that the pressure, we'll call it external. So that's the applied pressure. That's the pressure coming from outside. That's why it's called external. It's coming from this mass, which is outside the cylinder, is going to be equal to the pressure of the gases upward, right? So just like with forces, the external force, the weight, is equal to the force of the gases pushing up, and those collisions of the gas molecules with the with the piston, that's what causes it to move up. So that force upward, we can also do it in terms of pressure. The external pressure is equal to the pressure of the gases, okay? Why is that important? Because we can't necessarily easily measure the pressure of the gases. There are ways to do it, but it could be challenging. So what we do is we say, wait, if the piston is not moving, then that means the external pressure is equal to the pressure of the gases. So if we can measure the pressure, the external pressure, if we can measure that, that allows us to figure out what the pressure of the gases are, okay? And that you can do because pressure is weight divided by surface area, okay? Now, pressure comes in many different units. We're going to talk about this in chapter 10 more, but it has many units. Just like length has many units: inches, feet, yards, miles, centimeters, meters, kilometers. Same thing for pressure, has many units. So what are the most common ones? One is called atmospheres. And atmospheres has an abbreviation, ATM. And so one atmosphere, you might see this, for example, one ATM is essentially the pressure of our atmosphere at sea level. Okay, that's essentially what an atmosphere is. It's the pressure that we have with our atmosphere on the Earth. Okay, at sea level. So you might see pressure units there. What about volume? Volume has many different units as well: ounces, gallons, quarts, pints, cups. Those are all units of volume. In the SI system, we have the milliliter, we have microliters, we have liters, right? So typically for these types of problems, we're going to use the liter. And the abbreviation for that is an L. And so an example of that is a 2-liter bottle, right? If you buy a 2-liter bottle in the store, you know how big that is, right? That's 2 liters, okay? So liter is also a unit. So now what I'm going to do is I'm going to talk about the gas cylinder again in terms of work. So for the gas cylinder, the amount of work due to compression and expansion, right? We talked about that last week, that a gas cylinder, the piston can move up or down, so we can have expansion and compression. The amount of work is equal to a negative, so there's a negative in this formula, times P external. So I'm going to abbreviate external as EXT, times the change in volume, delta V, where delta V is the final volume of the cylinder minus the initial volume of the cylinder. And this is the equation we use for mechanical work of a gas cylinder. What it says is if a cylinder undergoes compression or expansion, we can calculate the amount of mechanical work, the amount of work that's done, by just using this simple little formula. We need to know what the external pressure is, and we need to know what the final volume is and the initial volume of the cylinder. Okay, so let me show you a little picture of that. So imagine, here's our cylinder. I'm going to do expansion to begin with. So here's our gases. And we have, some pressure coming down, pushing down, just pushing down on the gases. So this is external pressure. Okay. So this initial volume, even though I'm measuring, I'm kind of depicting it as a height. Okay. It's not, it's a height, there's a height to it, but it's actually a space, right? It's a volume. So it's the height times the surface area. Okay. So there you go. So now we would say, suppose we undergo expansion. Okay, so what does that mean to say expansion? What we mean is the gases are now occupying a larger volume. And what they're doing essentially is they're pushing that that piston up, right? So they're pushing against a force that's pushing down, and that takes energy to do that. It turns out that if there's no atmosphere above the piston, expansion will just happen and there's no energy change associated with that. But if it's pushing against a weight or an external pressure, that takes energy to do that. So kind of think of it this way. If you have something that has weight and you push up against it, it takes energy to do that. If the object that you're pushing is heavier, it takes even more energy to do that. So essentially what the gases are doing is they're pushing against this weight, this external weight or external pressure. Okay, remember pressure is force over area or work over area. Okay, so now what do we have? We have a final volume, right? We have a final volume here. We still have our gases in here. The assumption in this is that the external pressure is never changing. Okay, so the external pressure is constant during this process. Now, if the external pressure is the weight of the atmosphere pushing down, that's a pretty good assumption. If the external pressure is due to a little brick, that's a pretty good assumption because we wouldn't expect the brick to change its weight as it moves up. Okay, so there you go. So now the amount of mechanical work due to this expansion is minus P delta V, which is minus P for external, right? External pressure times V final minus V initial. Okay, very, very simple. Very simple formula. All you need to know are these two volumes, the initial and final, and the external pressure. Just don't forget to put that negative sign in there. Now, there is an issue with units. And the issue is that typically work has units of joules. And the unit joule is a capital J. We represent that, the abbreviation is a capital J, okay? But the issue here is that our pressure might be in atmospheres, and the volume might be in liters, L for liters, right? Well, that's a problem, right? Because an atmosphere in a liter is not the same as a joule. So let me just give you the conversion factor. And I'm not going to go through the derivation of this conversion factor. It's not that difficult, but it's just not necessary. We'll talk more about this a little bit when we get to gases in chapter 10. But 1 liter times atmospheres, which would be the units that you get here, right? Because this would be in atmospheres and volume would be in liters, is equal to 101.3 joules. Okay, 101.3 joules is the same as a liter atmosphere. Now, let me actually look this up. Of liter atmosphere to joules and see if there's any confirmation of this. So if you need to go even more sig fig, so sometimes Alex may want you to use more, it's 101.325. Okay, so if you just need 4 sig figs, it's this one. If you need 6 sig figs, it's this one right here, more sig figs, okay? All right, so that's a lot of background right there for the work of a gas cylinder. So what I want to do is I want to show you an example of this. So we're going to look at a problem where we actually calculate the amount of work for expansion or compression of a gas cylinder. So let me see if I've got one here. Yep, there we go. Okay. Okay. So calculating pressure volume work, or PV work, I called it earlier, right? So a mixture of nitrogen and hydrogen gas, so that's your gas mixture, is compressed from a volume of 80.0 liters to a volume of 79.0 liters. So that's a little change of volume, about 1.5% or 1.4%, while the pressure is held constant at 86.0 atmosphere. So we can't really do these problems if the pressure is changing. There is a way to do that if the pressure is changing, but it's beyond the scope of this course. So we will look at it only in the case of a constant pressure. So don't worry about having 2 pressures. Calculate the work done on the gas mixture. There you go. Round the answer to 2 significant digits and be sure you use the correct positive sign or negative sign. And I want to point out that if you get the right number, but you get the wrong sign, it's completely wrong. It's a 0. And the nature of this is it's sort of like being an accountant. If I say, oh, congratulations, you, at the end of the year, you have a profit of $500,000. And that was wrong. I'm sorry, I made a mistake. You actually owe $500,000. You lost $500,000. That would be an egregious error, right? So the same is true when we do thermodynamics or thermochemistry. The sign is actually more important than the number. If the actual value was 170 and it was negative 170, and you got the answer 168 negative 168, that's off a little bit, negative 168 versus negative 170. That's off a little bit. Number's not exactly right, but it's pretty close. That is much, much more desirable than negative 170 versus positive 170. You could say, well, wait a minute, I got exactly the right number, 170. But no, in fact, you're off by 340 because instead of going from negative 170, you're all the way up to positive 170. That's a difference of 340. So the sign is very important here.
In the case
When you do these calculations, make sure you've got the sign correct. Okay.
in the case of
All right. So let's take a look. Relatively simple question. The issue here they don't tell you what the units are going to be here, but I think when you actually fill in the answer, it has a little J for joules there. Okay. I will show you kilojoules as well. So let's stop share here.
In the case of compression, then we're doing a positive P, correct? Positive P times
All right,
the change
so
volume.
it's compression. So the gases
Not working. I think.
are compressed.
Professor, Sophia's trying to talk to you. I don't think you can hear her.
80.0 liters.
I don't think he can hear us.
I don't think so either.
79.0 liters.
It's really weird.
So
Okay.
let's find delta V. So that would be the final volume minus the initial volume, right? So it's going from here. So that's your initial where you're starting off. And it's going to 79. So that's your final volume. Okay. So delta V would be 79.0 liters minus 80.0 liters. And that's negative 1.0 liters. Okay. So there's your change in volume. The next thing they do is they tell you that the pressure is constant. At 86.0 atmospheres. Okay. Oh, okay. So that means P external is 86.0 liter atmosphere, sorry. So now we have enough information to solve this problem. The amount of mechanical work is negative P external times delta V. So that would be negative 86.0 atmospheres times negative 1.0 liters. Now notice you have the negative in the formula and then you have the negative in terms of the change in volume. So that's negative, right? I'm sorry, that's positive. Negative times negative is positive. So you actually get positive 86.0 atmosphere liters. Okay, so there's your work. But again, the units that we're going to use are typically in joules. So let's write down, let's convert to joules. Okay, so I'm going to take my positive 86.0 atmosphere liters. Okay, and I'm going to do our conversion. It's 101.325 joules per 1 atmosphere liter, or liter atmosphere. Sometimes people do it liter atmosphere, but atmospheres cancel, liters cancel, and you've got joules. Okay, so let's calculate that. 86 times 101.325, and it's a relatively large number. It's 8,000, I'll put a comma there, 713.95 joules. Now, sometimes when we have numbers that are in the thousands, it's convenient to convert from joules, which is J, to kilojoules. You'll see that, which is KJ. Okay, joules to kilojoules. So that's a relatively simple, that's right, because you just have 1,000 equals kilo. So 1 kilojoule is 1,000 joules. That's all that is. So if we take our 87, 13.95 joules and convert it to kilojoules, put the kilojoules in the numerator, put the joules in the denominator. That way you're doing not 100, but 1,000. You get 8.71395 kilojoules. And let's round that to 2 significant digits because the, oh, is it 3? Oh, it says 2, actually. Did they just say it was 86? Oh, I know, it's only 2 because our change in volume only has 2 significant digits. So it should be rounded to 2. So here's your most significant, here's your second most, so it's just 8.7 kilojoules. Okay. So it's actually probably better to have it in kilojoules than it's joules. If you were going to do it in joules, you would do 8,700. But even that is a little ambiguous. It seems to have two significant digits, but the zeros are ambiguous. So what you could do is put it in scientific notation. 8.7 times 10 to the 3, right? You just move the decimal point 3 places, and you got 8.7 times 10 to the 3 joules, okay? Kilojoules actually is probably a little easier because you just put 8.7, okay? All right, so there is your mechanical work there. It's actually called PV work because it is a type of mechanical work, but it's specifically for gas cylinder, okay? And that should be, so let me see. It looks like when you do this on Alex, they're using a bunch of significant digits for the conversion between joules and liter atmospheres. So the 101.325 or what, yeah, 101.325 was the correct one to use. Okay. All right. Now we're going to move on into something called enthalpy. So we're in section 5.3, and we're going to talk about enthalpy. And the symbol for enthalpy is an H. Okay. So let me talk just real briefly. I'm going to try to give you a little introduction into this idea of enthalpy. There are times when we can make some simplifications in our calculations. So if we look at our change in internal energy, right, and we said that's E final minus E initial. Okay. And we said that that was equal to Q plus W. So that is a measure, it's sort of an accounting of energy, how much energy is coming in, how much energy is going out. And what we're claiming is energy can come in two ways, come in the form of heat and go out in the form of heat. It can come in as compression or it can go out as expansion. Right? Those are two different ways of changing the amount of internal energy that these gases have. Now, what we're going to do is we're going to say the following. Suppose we're at constant pressure. And that is a requirement for this discussion of enthalpy. We're going to be at constant pressure. So that means that the weight of this block that's sitting on the piston is not changing. That's reasonable. And it also means, or it could mean that the atmospheric pressure is not changing. And that's reasonable as well. Generally, the atmospheric pressure doesn't change over a short period of time, at least not significantly. If you're in a hurricane, that might change, but under most circumstances, it's not. Okay, so constant pressure. So what I'm going to do is I'm going to define a new quantity of, actually, let me go back, a new quantity of energy. And I'm going to call it H for enthalpy. And you can kind of think of H as heat. And enthalpy is going to be defined as the amount of internal energy that the gases have plus pressure times volume, PV. Okay, so it's a very peculiar, very specific definition, and we do it for a very practical reason. We're defining this enthalpy with PV in it. Okay, it's the internal energy plus PV. Now, just like internal energy, we're generally not concerned about the amount of energy something has. We're concerned about how much comes in or goes out. So I'm going to define the change in enthalpy, delta H, as being the sum of the changes of both of these terms, plus delta, I'll put this in parentheses, delta PV. But normally we're going to look at problems where the pressure is constant. So I can rewrite this as delta E plus P delta V. It turns out, if pressure is changing, that complicates things. It's still soluble. It's still something we can solve, but it gets more complicated. So we're going to look at this situation here where the pressure is constant. So this is what we can use if the pressure is constant. Okay. Now, what I'm going to do is I'm going to do a little derivation for you, a very simple one. If we define enthalpy this way as delta E plus P delta V, okay? But now we have this earlier equation where delta E is Q plus W, right? Right. And we have this other equation that says W is minus P delta V. It's the negative of what we have here for our enthalpy definition. So what I'm going to do is I'm going to substitute in Q plus W, but for W, I'm going to put in our P delta V. I'm just using these earlier formulas. So now delta H would be Q plus W plus P delta V, right? Because this is delta E. But now I'm going to substitute in for W minus P delta V. And then I'm going to add the P delta V for our definition of enthalpy. So now you have three terms here, but notice the second and the third terms. They are the opposites of each other. They're the negative. They are the anti of each other. So they actually add up to 0. And you just end up with Q. And this ends up being very useful. What it says is we have this measure of how much energy a system has, a mixture of gases in this case. And if we're at constant pressure, then, and I'll put a little P here to indicate that it's at constant pressure, then instead of calculating delta E, instead of changing the amount of internal energy, the change in internal energy, I'm going to alternatively calculate the, sorry, let me plug this in. I'm going to calculate or compute the change in enthalpy, delta H. So enthalpy is useful for systems that are at constant pressure, okay? It is essentially a measure, again, of the amount of energy that a system has, or the change in energy that it has. Oops, let me move this up here a little bit. But it is more useful. Oops. Right. So I can't hear you. Okay, you can hear me though, right, Shamir? Okay, good. All right. So if you have a question, just put it into the chat, okay? Let me just put this up here. I should be able to hear it, but for whatever reason I can't. Okay. Sorry that I didn't see your message until earlier. Okay. Okay. Yeah, if you have a question, just put it into the. Okay, that's fine. Okay, so now what I'm going to do is I'm going to come back and look at a problem. So let's bring this over here. Okay, so understanding the definition of enthalpy here. Measurements show that the energy of a mixture of gaseous reactants increases by 352 kilojoules during a certain chemical reaction, which is carried out at constant pressure. So there's our constant pressure, right? Furthermore, by carefully monitoring the volume change, it is determined that 167 kilojoules of work is done during the reaction. Calculate the change in enthalpy of the gas mixture during the reaction and round to 3 significant digits. And then is the reaction endo or exothermic? So pay attention to what they're telling us here. It's very similar to the gas cylinder problem we did last week. They're telling us the energy increases. So increases is a positive change. 352 is the amount. Kilojoules is the units, not joules, but kilojoules. Energy. So what are they talking about? When they say energy, they mean internal energy. So that's your delta E. So they're telling you delta E is 352 kilojoules positive. During a reaction carried out at constant pressure, okay? By carefully monitoring the volume change, it's determined that 167 kilojoules of work. So W, work is 167 kilojoules, and it's done on the mixture, so that's a positive, right? Our convention is if work is done on the gases, that's a positive W. If work is done by the gases, that's a negative W. Calculate your enthalpy change, right? Change in enthalpy, which is our delta H. And then is it endo or exothermic? Okay. So let me go through and show you this one. This one's actually relatively simple. It's just a matter, again, it's a word problem, right? So what they're saying is that your change in energy, so they're saying delta E is positive. It increases, so that's positive 352 kilojoules, okay? Then they're telling you it's a constant pressure, and they're telling you that the work is done on the gases, so that's positive, okay? Done on gases. So that's positive, and it's 167. And then they're asking you for the change in enthalpy. Well, let's go back to our equations. We have delta E equals Q plus W, right? So we know delta E and we know W. What can you calculate? You can calculate Q. So let's just rearrange this. Let's just say Q is delta E minus W, right? So that would be 352 kilojoules minus 167 kilojoules. Okay, so 352 minus 167, and you get 185. But that's not what the question was. The question was, what's the enthalpy change? Oh, but that's actually an important point here. It's at constant pressure. Right? This is done at constant pressure, and that means delta H is equal to Q. And what we do is we put a little P down there to indicate it's at constant pressure. Okay, so that means that's equal to 185. Okay, so these two formulas right here, this one right here, and then this one, that's all we need for that problem. That's going to give us our units. Now, remember the terminology, exothermic versus endothermic. Well, we can use, since delta H equals Q, we can use the same sign convention, right? It's not like delta H equals negative Q or, they're equal to each other. So whatever the sign convention for heat is, the sign convention for enthalpy changes as well. And what we said was that if it's positive, it's endothermic. And if it's negative, it's exothermic, right? And this is the case where heat is released by the system. And this is where heat is absorbed by the system. Okay, so it's positive, so that means it's endothermic. Right there, that tells us this is an endothermic process. Okay, and that is essentially that type of problem. It's relatively simple. You just have to have these two formulas here, delta equals Q plus W. And then again, if it's at constant pressure, that's going to be the case. So we normally look at constant pressure situations. We're not going to look at too many non-constant pressures for these problems. Okay, so let me see. I'm just going to look real quickly and just see if there's any that are significantly different. Oh, okay. Here's one's a little bit, it's the same problem, but they changed it up a little bit. So let me show you this one. Okay. I won't go through this one completely. I'll just kind of talk you through it. Measurements show that the enthalpy of a mixture of gaseous reactants decreases by 374 kilojoules. So enthalpy, that's delta H. So they're telling you delta H is 374. Decreases. So what's the sign if something's decreasing? It's negative, right? Decreasing is negative. So delta H is negative 374 during a chemical reaction, which is carried out at constant pressure. So again, enthalpy, we can talk about enthalpy. Delta H is equal to Q under those circumstances. Furthermore, by carefully monitoring the volume change, it is determined that 53 kilojoules of work is done on the mixture. So again, the sign of the work will be positive because it's being done on the mixture. If it said that it was being done by the mixture, then it would be negative, work would be negative, but it's being done on the system, on the gases. So W is positive 53 kilojoules. So what do we have here? We know what delta H is. We know what W is. But we also know that delta H is equal to Q because it's at constant pressure. So not only do we know delta H, we know Q is negative 374. Q is negative 374. We also know that W is positive 53. So W is positive 53. Q is negative 374. Look at the question. What's the change in energy of the gaseous mixture? Well, that's delta E. So delta E we can find from delta H and we can find from Q, right? Because delta H is Q and delta E is Q plus W. So we have Q, we have W, we can find delta E. Now the exoendothermic, again, that is related to the enthalpy change. Because delta H is equal to Q, we use the same sign convention. So if delta H is negative 373, as it is in this case, then that's an exothermic process, okay? So exothermic is when delta H is negative or when Q is negative, both of them, okay? So there you go. So there's a second example of one of those problems. Now, let's take a look at the next topic here, which is getting it into chemistry. So that was all physics and engineering. It's really just engineering what we just did there, although they teach it in physics. What we're going to look at now is we're going to look at some chemistry. And we're going to connect this discussion to chemistry for the first time. Okay, so let me show you this one. Using the general properties of reaction enthalpy. So there's our delta H, right? A chemist measures the enthalpy change delta H during the following reaction. 2 waters, liquid, plus oxygen gas forms 2 H2O2 liquid, which is hydrogen peroxide. So water plus oxygen to form hydrogen peroxide. And delta H is given 196 decimal kilojoules. Use this information to complete the table below. Round each of your answers to the nearest kilojoule per mole. Okay, so a lot of chemical equations in here, right? So this is where we're relating all of this discussion to chemistry. Now, very briefly, what happens is in chemistry, we're mostly concerned with delta H because we're going to measure energy at constant pressure under many circumstances. We don't always do it under constant pressure. So for those of you that have taken nutrition classes, you realize that there is this idea of energy content of foods, right? So some number of kilocalories of energy is associated with foods, like proteins and carbohydrates have 4 kilocalories of energy per gram. And I'm sorry, yeah, kilocalories of energy per gram. And fats have 9 kilocalories of energy per gram, and alcohols have 7 kilocalories per gram. So that's an energy content, right? So those measurements, those numbers 4, 7, and 9 those are not done at constant pressure. Those are done at constant volume. So there are cases, and if you take advanced chemistry courses like physical chemistry, you'll look at how we deal with the issue of reactions that are not occurring at constant pressure, because it does happen. But for the most part, we're just going to focus right here on constant pressure, just to keep things sort of simple. And if we're measuring things at constant pressure, then really what we're going to be interested in is delta H, because delta H is equal to Q at constant pressure. Okay, and that's what makes it useful. That's why we moved away from talking about delta E, the change in internal energy, into talking about delta H, which is the enthalpy change. Essentially, imagine you're running like a little reaction, like a titration or something, acid-base titration, like vinegar, right? So you got an acid in here, and you're adding a base to it, right? Acid plus base. That's going to be done open to the atmosphere. This is at constant pressure. So if we're concerned about the energetics, the energy, the thermochemistry of this particular reaction, we have this very simple relationship here. All we have to do to find the change in energy, the change in enthalpy of this system is to measure Q sub P. And we haven't done that yet. We haven't really looked at how we measure Q. We're going to talk about that in the next section. We'll talk about that tomorrow. But suffice it to say, this is easy to measure, very easy to measure. You can do it in your kitchen. So if that's easy to measure, that makes this easy to measure, right? Because they're equal to each other. Delta E, not so easy because it's Q plus W. So how do you measure this? That's not easy to measure. Generally, for the reactions that we're looking at, like this one right here, W is very, very small. It's almost zero. So we can usually neglect it. But in a sense, this is the reason that we're going to use delta H, is because it's so easy to measure if we're at constant pressure. The pressure changes, that's all. Okay. So how are we going to deal with this? So generally what we're going to do is I'm going to introduce something called a thermochemical equation. And it's like a chemical equation. In fact, it says chemical equation. It's just that it's thermochemical. So there's an additional aspect of this equation. So an example of this would be here. Here's the thermochemical equation. A thermochemical equation is balanced. It's a balanced equation, and then it's going to have delta H associated with it, something that has been measured. Okay, so minus 285.8 kilojoules per mole. Okay, so this is called this is an example of a thermochemical equation. It shows you a balanced equation, so that's the chemical equation part, but someone has measured this. So someone in a laboratory has measured this value and they're telling you what the value is. Okay, so it'd be like if you were looking at a price listing for a house. Here's your address, here's the price of the house, right? Same idea. You have a chemical equation that's balanced, and then you have an associated enthalpy change delta H for it. Okay, and that's called a thermochemical equation. And these are very useful. What this tells us is that if we have 1 mole of H2 gas and a half, 0.5 is a half, moles of O2 gas, and they react to give us 1 mole of liquid water, this tells us how much energy is released. So this is the enthalpy change. It's the enthalpy change of the reaction. Essentially, it's the energy released by the reaction. Okay, so by telling or by giving us the thermochemical equation, they're not only telling us what the reaction is, what the materials are, they're telling us how much energy is exchanged in that particular reaction. So this is negative, right? So it's exothermic, right? So that's the energy that's going to be released. If it were positive, it would be absorbed, right? But if it's negative, delta H is equal to Q, then this is the amount of energy that's released. So imagine you saying, hey, I want to heat my house. And I have 2 ways of doing it. So I'm going to show you a second one. Okay, so you look at this and you say, okay, you got this one up here. It's giving me 286 kilojoules of heat. This one right here is giving me 86 kilojoules of heat. Which one am I going to go for? I might want to go for this one, right? This one's giving us more heat. It's giving us more energy. So hydrogen and oxygen to form a mole of water. I didn't balance this. This is a 2 here. Sorry. That's going to give us more energy. In terms of weight, if you think about it this way, how much does a mole of hydrogen weigh? It only weighs 2 grams per mole, 2.02. How much does methane weigh? CH4. Well, that's going to be carbon plus 4 hydrogens. That's about 16.05 grams. So this weighs more, right? So in terms of weight, you get more energy out of this because it only weighs 2 grams here. And this one weighs 16 grams. You're only going to get that much energy. So this would be a preferable reaction. In fact, many people believe that this would be probably the best way to heat things, would be to use hydrogen and oxygen. The problem is hydrogen is such a small molecule, you can't store it very easily. If you try to put it through a gas pipeline like we put natural gas, remember this is natural gas here. This is what all those hundreds of thousands of miles, maybe millions of miles of gas pipelines throughout the whole country and around the world, that's all pushing natural gas right through the pipes, right? This comes from the atmosphere. So it works, you get some heat out of it. It's not bad, it's okay, it's actually pretty good. But this would be better. But the problem is hydrogen is such a small molecule that if you look at the atoms of iron, which is what you're going to make your pipes out of, steel, right? Or plastics even, whatever you make your pipes out of, the hydrogen molecules can actually escape because they're so small. Those hydrogen atoms are so small they can get out. So you're trying to, give people hydrogen gas, it's coming out. So they have some more exotic ways of storing it, but it requires exotic materials and it's not so easy. People are definitely working on that problem though, because if you think about it, you're getting about 3 times as much energy out of the hydrogen as you're getting out of the methane. And there are ways to produce hydrogen from water. So there are ways to do the reverse reaction. But in any case, these are called thermochemical equations, and they associate the energy change with the chemical equation. All right, so let's come back to this problem, and I'm going to show you this example. Really, this is a very simple problem. What they're asking you to do is to take the given thermochemical equation with the delta H value. This is all given here. And then they're asking you to do something to the equation. You're going to change this equation in some way. And there's only really 2 ways you can change it. You can either reverse the equation, so make the products reactants and make the reactants products. So notice, for example, this one right here has H2O2. Well, this one does too. Let's take this one, this middle one. H2O2 is now a reactant. And then H2O and oxygen are products. So these are now products, and this is reactant. That's called reversing the equation. Products become reactants. So the question is, what happens to delta H if you reverse the equation? You just change the sign. So, energy goes in or it goes out. If it's coming in, it's positive. If it's going out, it's negative. So if this is positive over here, reversing the equation just makes it negative. That's all it does. The second change you can make is you can multiply these coefficients by some number. If you multiply all the coefficients by the same number, it's still going to be balanced. If you double everything, it's still balanced. If you multiply by a half, everything is still balanced, as long as you do it to everything in the equation. So in a couple of these problems, what they're doing is they're multiplying these coefficients by some number. So for example, see how this one is a 2, but now it's a 6? What do you multiply a 2 by to get a 6? It's a 3, right? 2 times 3 is 6. So what they did here is they took this equation and they multiplied it by 3 to give us a 6. They took a 1, multiplied it by 3 to get a 3, and they took a 2 and multiplied it by 3 to get a 6, okay? So they're going to multiply these coefficients by the same number. They're not going to multiply this one by 3 and this one by 2. It's going to all by the same number. So you just have to look really at one of them. So if this goes from 2 to 6, it multiplied it by 3. So what happens to delta H? If you multiply the balanced equation by a number, you multiply delta H by the same number. So if you multiply this equation by 2, so this becomes a 4, a 2, and a 4, you just multiply this by 2 and it becomes, 392. If you multiply this by half, this becomes a 1, a half, and a 1. You multiply this by a half and it becomes 98. That's all you got to do. So really, it's a little puzzle. What you're doing here is you're saying, what did they do to this equation to make it this one? Well, let's take a look at the first one. This is a 6, this is a 2. So they multiplied it by 3. They didn't change the direction at all. It's still water on the reactant side. It's still oxygen on the reactant side. it's still hydrogen peroxide on the product side. So they just took this equation, multiplied it by 3. So you would take 196 and multiply that by 3. So 196 times 3, 588. So this one would be positive 588. In the second one, it looks like now the H2O2, which was on the product side, is now on the reactant side. The coefficient is still the same. They didn't change the coefficient. So they didn't multiply by any numbers. They just changed the direction. So just changing the direction, we call that reversing an equation. What that means is you just change the sign. So instead of positive 196, it now becomes negative 196. Okay. And the last one, what they're going to do is they're going to do both together. They're going to reverse it perhaps and multiply by number. That's how I would kind of think about it logically. Multiply by equation to get that skill, reverse the equation to get that skill, and then combine the two together to get a combination of those two skills. So let's look at the third one. This one has H2O2, but it's on the wrong side. So that means they reversed it. So instead of being 196, it's negative 196. But clearly this is not a 2 anymore, right? This is now a 1. So that means they multiplied it by something. So to go from 2 to 1, what do you have to multiply 2 by to get 1? 2 times 1 is 2. 2 times 2 is 4. So it's not 1 or 2. 2 times a half is 1. So it looks like what they did was they took the 2 and multiplied it by half to get 1. So let's check that. This was 2H2O, now it's 1H2O. So they multiplied it by half. This is O2, now it's half O2. They multiplied by half, right? So again, whatever they multiply one of the coefficients by, they're going to multiply all the coefficients, because otherwise it wouldn't be balanced anymore. So it looks like this one was reversed to make it negative 196, but then it was multiplied by half. So that would be negative 98. Okay, so that's one aspect of enthalpy that we want to use, is this idea that if you reverse an equation, you change the sign of delta H. And if you multiply the equation by some constant in the balanced equation, you multiply delta H by that same value. So you'll try this one as well. Okay. So tomorrow what we'll do is we'll wrap up our enthalpy. We have one more type of problem to do, which is sort of a stoichiometry type problem, mass to mole conversion. So we'll come back to that. We'll look at that, wrap up our enthalpy. And then the next section is 5.4. That will be getting into this idea of calorimetry. Okay. I'm going to go ahead and stop share. I'm going to stop the recording.